Good morning everyone. Today I will focus a concept revision of chapter continuity and differentiability through questions. Here first we revise result of continuity and differentiability. Limit of fx extends to a minus limit of fx extends to a plus equal to fa. Unique definite real number implies and implied that function is continuous at x equal to a. Continuity in closed interval AB means continuous at left end, means right hand limit at A and functional value at A. Should be finite real number. Continuity at B means left hand limit at B and functional value at B. Should be finite real number and continuous at each intermediate point, that is open interval AB. Differentiability at a point LF dash A, limit h tends to 0, fa minus h minus fa upon minus h. Right hand derivative at A, Rf dash A, limit h tends to 0, fa plus h minus fa by h. If both will be equal and should be finite unique real number, then f is differentiable at point x equal to A. And now we take a question here. Which of the following function have removable discontinuity at x equal to 1? Removable discontinuity at x equal to 1. We know definition of removable discontinuity at a point. Limit should be exist. Limit of fx x tends to a should be exist finitely, but not equal to functional value, where functional value either undefined or if defined but not equal to limiting value. Here we have to check removable discontinuity in 4 cases. First we take here fx equal to log of mod x. Here left hand limit of fx x tends to 1 minus log of mod x around 1, x less than 1, x less than 1 or x greater than 1. In both case x is positive. So log of mod x equal to 1 upon log x in neighborhood of point A. So left hand limit at A, limit x tends to 1 minus 1 upon log mod x, limit x tends to 1, 1 upon log x. Here x tends to 1 from left. Here x tends to 1 from left. Corresponding value of log x tends to 0 from below. Obviously this tends to 0 from left side. Again when x tends to 1 from right, x tends to 1 from right, corresponding value of log x tends to 0 from right. So 1 upon this tends to 0 from right. Clearly limit of fx x tends to 1 does not exist in this case finitely. Our main concern is here for removable discontinuity. Limit must be exist at that point. Here limit does not exist, so no removable discontinuity in this case. The first case is rejected. Second, fx x square minus 1 by x cube minus 1, x plus 1 x minus 1, x cube minus 1 x minus 1 into x square plus x plus 1. If x not equal to 1, cancelling these two factor, x plus 1 upon x square plus x plus 1. So left hand limit of fx x tends to 1 minus, this is 1 plus 1, 1 plus 1 plus 1, 2 by 3, and right hand limit x tends to 1 from right fx, again equal to 2 by 3. Here limit of fx x tends to 1 exists finitely. So this is the case of removable discontinuity. Here B is the solution. Third case here fx equal to 2 to the power minus 2 to the power 1 upon x minus 1. We write here 1 upon 2 to the power 2 to the power 1 upon x minus 1. Here, left hand limit h tends to 0. We write x in place of x 1 minus h, 1 upon 2 to the power 2 to the power 1 upon 1 minus h minus 1, cancelling, minus 1 plus 1 upon minus h tends to 0, 1 by h tends to infinity, minus 1 by h tends to minus infinity. So 2 to the power minus infinity, 1 upon 2 to the power infinity, 1 upon infinity, that is 0. So this become 1 upon 2 to the power 0, that is 1. When our limit h tends to 0, we replace x by 1 plus h, or this tends to 0. Here limit does not exist, so this is not the case of removable discontinuity. And our fourth option is fx under root x plus 1 minus root x upon x square minus 1. Rationalizing and cancelling numerator and denominator common factor, minus 1 upon x into under root x plus 1 plus under root 2x. Left hand limit at x equal to 1, this will give minus 1 upon 2 root 2, and right hand limit at x equal to n, again 1 upon minus 1 upon 2 root 2. Here left hand limit, right hand limit, both are finite and equal. So limit exists, and this is the case of removable discontinuity. So in this case, we have to answer B and D. Next one is let fx x minus 4 upon mod of x minus 4 plus a x less than 4. A plus b when x equal to 4, x minus 4 upon mod of x minus 4 plus b, x greater than 4. Then f is continuous at x equal to 4. When a 0, b 0, a1, b1, a minus 1, b1, a1, b minus 1. Here, continuous as at x equal to 4. This implies L equal to R equal to B. Left hand limit, right hand limit, value. This is the point 4. X less than 4, x greater than 4. In this case, x minus 4 less than 0, or in this part, x minus 4 greater than 0. So, left hand limit of fx x tends to 4 minus limit x tends to 4. In this case, x less than 4. And we have, if x less than 4, x minus 4 is negative. So, modulus of x minus 4 is minus of x minus 4. This is minus 1. X minus 4 upon minus of x minus 4a. Limit x tends to 4 minus 1 plus a. This is a minus 1. Next, right hand limit. Limit of fx x tends to 4 plus. Limit x tends to 4. When x greater than 4, x minus 4 is positive. We have x greater than 4, definition of function is this. So, x minus 4 upon x minus 4, that is 1 plus b. 1 plus b, this is constant, so 1 plus b, and value equal to 1 plus b. Taking L equal to v, this will give a minus 1 equal to a plus b. This implies b equal to minus 1. R equal to v, this will give 1 plus b equal to a plus b, cancelling b and b. This will give 1 equal to a equal to 1. So our answer is a equal to 1, b equal to minus 1. That is answer D. The third question is, if fx equal a mod of sin x plus b e to the power mod fx plus c mod x cube, and f is differentiable at x equal to 0, then a, b, c, all three are equal. A equal 0, B equal to 0 and C belongs to R. B, C both 0 and A belongs to R. And fourth is C0, A0 and B belongs to R. Here A mod x mod sin x, B E mod x plus C mod x whole cube. We know generally modulus function differentiable at their root in many cases. Here we use transformation of graph, alternatively analytical formula or properties of continuity differentiability. Here first, transformation of graph, we already know about this, fx to modulus of fx. We retain the portion of curve above x-axis as usual. Remove the portion of curve below x-axis. Here we take a graph of function like this. Portion of curve above x-axis we have to keep as usual. Remove the portion of curve below x-axis. Here we keep as usual and remove this portion, and we take this portion, image of this portion in x-axis, that is we rotate this portion about x-axis in through 180 degree. So this is the graph of mod of fx. Similarly, fx2, graph of f of mod x, as for example 2 to the power x, 2 to the power mod x, 2 to the power minus x, 2 to the power minus mod x, sin x, sin of mod x, etc. We see here, if x greater than equal to 0, f of mod x equal to equivalent to fx. When x less than 0, f of mod x equal to f of minus x. Means x greater than equal to 0, that is right side of y-axis, we have to keep the original curve fx. Remove the portion of curve below x-axis, left of y-axis. Here, this is the graph of y equal to e to the power x, and we have to shift e to the power mod x. So here we keep the portion of graph to the right of y-axis as usual, that is this portion remains same like fx. We remove this portion, remove this portion. Now we take the image of right part about y-axis through 180 degree. Image of this, if we consider y-axis as a line mirror, image of this will be this. The graph of e to the power mod x. Clearly here, tangent through at this point 0, 1 through the right this line, and through the left this line. Obviously two different tangent, so not differentiable at x equal to 0 by graph. Analytically, so not differentiable at x equal to 0. So here e to the power mod x is not differentiable at x equal to 0. Here mod of sin x. Here graph of sin x like this, graph of sin x like this. We have to find the graph of mod of sin x. We keep portion of curve, sine curve above x-axis as usual, that is this part. We cancel this part and take its image in x-axis, that is this part will be shifted in this way. So this becomes this part and this part shifted to this part. So graph of mod of sin x is this, like this. Obviously these are the points x equal to n pi, where n is equal to 0, plus minus 1, plus minus 2, 0, pi, 2 pi, 3 pi, minus 2 pi. Here corner point, different tangent, corner point, different tangent, corner point, different tangent. So mod of sin x is not differentiable at these points. So in question, first term mod sin x is not differentiable. E to the power mod x is again not differentiable. Now we see mod x whole cube. Here e to the power mod x analytically, when x greater than equal to 0, fx ex, x less than 0, e minus x. Clearly, when x equal to 0, e to the power 0, 1. When x greater than 0, right hand limit, e to the power 0, again 1. And when x less than 0, e to the power 0, again 1. Function is continuous at x equal to 0. We know that if function is continuous at 0, continuous at a point, so it may differentiable or not differentiable. So the shortcut method we know, be differentiating both the side, f dash x, ex, x greater than 0, and minus e minus x, x less than 0. So left hand derivative at 0, that is left hand derivative at 0, that is minus e to the power 0 minus 1, and right hand derivative at 0 equal to e to the power 0, that is plus 1. Here left hand derivative minus 1, right hand derivative plus 1, both are finite but different, so not differentiable at x equal to 0. Y equal to e to the power mod x. If we use this part for time saving, next one, fx equal to mod x cube, we can write modulus of x whole to the power n, x to the power n mod, both are same. So mod x whole cube and modulus of x cube both are equal. Using graph, this is the graph of y equal to x cube. In objective question, we generally try to save time, more and more question in limited time, so we prefer here, if possible, we take help of a respective graph. Here y equal to x cube, this is the curve. If we shifted to mod of x cube, we remove this portion and take its image about x-axis. Here curve is this, curve is a smooth at 0, so differentiable at x equal to 0. So graphically we conclude here mod x cube is differentiable at x equal to 0. If we want to do with formula, so first remove modulus x greater than equal to 0, fx equal to x cube, x less than 0, mod x minus x, so minus x cube minus x cube. Here left hand limit, right hand limit value at 0 are same, so continuous at x equal to 0. We check differentiability by differentiating here f dash x 3x square x greater than 0 and minus 3x square x less than 0, L f dash 0, L f dash 0 minus 3 into 0 square 0 and R f dash 0 3 into 0 square 0. Here left hand derivative, right hand derivative both are equal, so differentiable at x equal to 0. Now we come to question. Here this is not differentiable, this is not differentiable, this is only this term is differentiable. Question is function is differentiable at x equal to 0, so necessarily a must be 0, b must be 0 and c may be any real number. Here a equal to 0, b equal to 0 and c, a equal to 0, b equal to 0 and c be any arbitrary real number. In such case function will be differentiable at x equal to 0. Otherwise sum of differentiable and non-differentiable function is always non-differentiable. So here answer is a equal to 0, b equal to 0 and c belongs to any real number. To do objective question, we prefer graph to solve the question if possible. Otherwise we have alternative method, analytical method using formula or properties. That's it. Our fourth question is if fx x to the power a sin 1 by x, x not equal to 0 and 0 when x equal to 0 is continuous but not differentiable at x equal to 0, the interval of a will be, first of all, continuous at x equal to 0, limiting value and functional value. F of 0 is 0 and right hand limit x tends to 0 plus x to the power a sine 1 by x. Continuous at x equal to 0. So we must have right hand limit, left hand limit both equal to function value. That is, this must be 0 here. If a equal to 0, in such case this becomes sine 1 by x, so limit does not exist. If a less than 0, in this case x comes down in denominator and this will be of the form 0 by infinity, that is, this will become undefined. So a must be greater than 0. So here right hand limit equal to value of function, that is 0. This implies a must be greater than 0. Similarly, left hand limit x tends to 0 minus x to the power a sine 1 by x, limit x tends to 0 minus s to the power a sine minus 1 by h, this minus sign here, minus s to the power a sine 1 by h. Again, if a greater than 0, in such case this becomes equal to 0, otherwise limit does not exist. So function is continuous at x equal to 0. We have a must be greater than 0. Next, we write differentiability at a point f dash 0, limit h tends to 0, f0 plus h minus f0 by h. Here f of 0 equal to 0 and fh s to the power a sine 1 by h, s to the power a sine 1 by h minus 0 divided by h. So limit s tends to 0, s to the power a minus 1 sine 1 by h. Clearly, if a minus 1 greater than 0, in such case this equal to 0, a finite definite number, so function differentiable at x equal to 0. When a minus 1 equal to 0, in such case sine 1 by h, only we have factor sine 1 by h, so limit does not exist, and f dash, that's imply f dash 0 does not exist, so not differentiable. Here f is not differentiable at 0, we must have this power a minus 1 less than equal to 0. Here f dash 0 will not exist if a minus 1 less than equal to 0, a, that is a less than equal to 1. So f is continuous but not differentiable, that is a greater than 0 but a less than equal to 1, that is a belongs to open interval 0 to 1 including end point 1. Here the answer is option C, a belongs to 0 to 1, open at 0 left end and close at right end.